Good morning everybody. In today's class we are going to see plane of symmetry, improper axis of symmetry and center of symmetry, examples and explanation. These are all coming under types of symmetry elements. Plane of symmetry, that is denoted by the letter sigma. Plane of symmetry is an imaginary plane which divides a molecule into two equal halves, and the reflection about the plane produces an equivalent configuration. That is, if we reflect the molecule about any plane, if it gives a equivalent configuration, then we can say that that molecule possesses plane of symmetry. The reflection plane can be classified into three types depending upon their relationship with the principal axis. One is the vertical plane, another one is dihedral plane, and third one is the horizontal plane. Vertical plane, sigma v, is the plane containing the principal axis or passing through the principal axis. Second one, dihedral plane, a plane bisecting the dihedral angle between two sigma v planes. Horizontal plane or sigma h is a plane which is perpendicular to the principal axis. All planar molecule possesses one horizontal plane, and any number of sigma v planes may be present depending upon the n value. Say for example, water molecule. Water molecule has two vertical planes because the order for water molecule is 2, n is equal to 2. Two vertical planes. For example, here we consider z-axis is the principal axis and molecular plane is the yz plane, and therefore the two vertical planes contains z-axis. One is the sigma v xz plane, another one is the sigma v prime yz plane. Sigma v xz plane, it's a plane passing through oxygen. Therefore, when we reflect through this plane, the hydrogen 1 comes to this side, right hand side, and H2 comes to left hand side, and the y coordinate changes its sign. When we reflect through sigma v yz plane, a plane containing all the atoms, molecular plane, all the atoms, they do not change their position, oxygen, hydrogen 1, hydrogen 2, but only the x coordinate changes its sign, but we will get the equivalent configuration. Therefore, water molecule possesses two vertical planes. Ammonia molecule possesses three vertical planes. One of is the principal axis is the C3 axis passing through nitrogen, and all the three vertical planes contains this principal axis, but they contain nitrogen and any one of the hydrogen atoms. That is, each of these planes pass through a nitrogen and hydrogen bond and also present in between other two hydrogen atoms. Therefore, first sigma v, one plane means a plane containing principal axis, nitrogen and hydrogen 1. When we reflect through this nitrogen and H1 do not change their position, but H2 and H3, they shifted their positions. 2 will come here, 3 will come here, equivalent configuration. Similarly, ammonia has got two more vertical planes. The second plane is the plane containing nitrogen and H2 and passing through this principal axis. Therefore, the H1 and H3, they will interchange their position when we do reflection. Similarly, the third plane is the plane containing nitrogen and H3. H1 and H2 will change their position when we are reflecting through sigma v3. Next, we consider a square planar molecule ICl4. Here, one of the vertical plane is plane passing through iodine and these two chlorine. This is one sigma v plane, vertical plane, and this one is another vertical plane, and this plane which bisects two sigma v plane is said to be a sigma d plane, Similarly, this plane bisects these two sigma v planes and dihedral plane. Therefore, in the square planar molecule, we have, since the planar molecule, the plane of the molecule itself, one plane of symmetry, molecular plane sigma h, and there will be two sigma v planes and there will be two sigma d planes. If the reflection is carried out twice on the molecule about the given plane, we get the original configuration. That is, sigma to the power 2 is equal to identity. Hence, a mirror plane generates only one distinct operation. Sigma to the power k is equal to sigma if k is odd. Sigma to the power k is equal to e if k is even. Now coming to improper axis of rotation. That is denoted by the letter Sn. This is nothing but rotation of a molecule about an axis followed by reflection in a plane perpendicular to the principal axis. That is denoted by the letter S subscript n. And Sn axis generates n operations when n is even and 2n operations when n is odd. That is, the symmetry operation of Sn axis, if n is even, they are Sn to the power 1, Sn to the power 2, etc. up to Sn to the power n, which is nothing but identity. Till we get identity operation, we can do a number of Sn operations. But in the case of Sn axis with n is equal to odd, we will get identity only when Sn to the power 2n is equal to identity. Therefore, we get 2n operations. Sn to the power 1, Sn to the power 2, etc. up to Sn to the power 2n. Example for S2 axis of symmetry is biphenyl. Both the phenyl groups are not on the same plane. Then example for, and also S2 is equal to I. It is said to be I inversion. How we can prove S2 is equal to rotation followed by, mathematically while we are doing the, while we are writing, we have to write the first operation on the right hand side, then next operation. Therefore, S2 is rotation followed by reflection. If we are rotating through Z axis, reflection through a plane which is perpendicular to this Z axis xy. Therefore, if we choose a point x1, y1, z1, while we are rotating through C2Z, Z will not change their position, but x and y will change their position, sign. Okay. Then while we are reflecting, Z axis is not there, therefore that changes its sign. These two remain minus x1. Therefore, here from original to this one, if we see, all the coordinates have got a negative sign. That means inverted. This is nothing but inversion. Therefore, S2 is nothing but inversion. Then next example, S3 axis, BF3 molecule. We are rotating through 120 degree, therefore 3. With respect to Z axis, axis passing through only boron. Then we are reflecting in a molecular plane, okay, a plane containing all the atoms, that is XY plane, and we will get the equivalent configuration. Associated operations of S3, for example, S3 till we get identity, we can proceed. S31 means C31 and sigma H1, C3 into sigma H. S32 means C32 sigma H2. Sigma to the power 2 is identity, therefore C32. S3 to the power 3 na, C3 to the power 3, sigma H to the power 3. This is odd, therefore we can say sigma H, and identity this one. S3 to the power 4, C3 to the power 4, sigma H to the power 4, C3 3. Final answer is C3 1. Finally, for S3 6, we will get identity. Similarly, we can write for the remaining operations. Inversion symmetry I. Next type of symmetry element. If a point exists in the center of a molecule such that identical atoms are found on either side at equal distance from it, then the central point is called the center of inversion. The operation involves inverting the position of vectors of each atom, that is x comma y comma z, to minus x minus y minus z, inverting the position of the atom. All homodiatomic molecules HH, if we choose the center of the point, then at equal distance it can meet the identical atoms. BR like that way. Similarly, a triatomic molecule means carbon dioxide center, you choose this point, oxygen. When we invert it, this equivalent configuration we will get it. Trans N2F2. Here, if we choose the center of the point at equal distance, it meets identical atom. Another example for molecule possessing center of inversion is octahedral AB6 type molecules, S6 molecule. These are square planar. These 4 are in the equatorial position and these 2 are in the axial position. Thank you.